So it's my pleasure to be here. I'm a lecturer at the University of Sheffield. I think this is a really high-level presentation, and I think it might be the wrong audience. Let's see how it goes. So these are some of the people that, of course, I have the pleasure to work with for this work. So this introduction will look ridiculous to all of you, but let's start. So when I think about machine learning, of course, we have some data, we have the model, and these models makes prediction, and what we like to think is that the distribution of the training data is really similar to the distribution of the test data. And these can become quite problematic, for instance, when we do not have enough data for the domain that we are working on. And the typical example of this, at least that I encountered in my research, that is more toward application, is when we work with biosignals. So in this case, we record the nervous activity from the forearm of a user, and we want to translate that thanks to a machine learning model to the intended actions, to the intended actions that the user wants to do. And of course, here the challenges are that we are in resource-constrained settings, so we cannot use large models. We need the models that is deployable at the edge. At the same time, there are distribution shifts because every time you mount your sensors, the distribution changes, and also the distribution shift because of different users. And these are some examples of typical actions, gestures that you can have. So of course, we want to let's focus first on classifying this. And this is the typical setting. So you train on some sessions, and then you test on some data from the same sessions that you have trained on. This is called inter-session accuracy or inter-session performance. But also you want to test on new sessions that you have not seen the data. And this is called inter-session generalization. And typically a lot of papers in the literature, what they do is that they do not report, they skip completely inter-session generalization because things do not work well. And models can fail quite badly. So I'll tell you a really simple way in which we tackle this problem. And at the beginning, when coming from machine learning and trying to apply machine learning for this application, I was thinking immediately to test time training, right? Where you have a self-supervised cost function, a test time that you constantly do, because of course you might not have labels at test time. But it's not super easy to define self-supervised loss when you have really highly noisy data, and you do not have any labels, and your data comes as a continuous stream of information. So we started at the beginning with simple alignment strategies. So long story short, simply on this task we could reach much better performance than much bigger models that were pre-trained on a lot of data simply by doing some alignment. And our models were more than 100 times smaller. So the first thing that we tried, of course, is a formal adaptive batch normalization. This is one of the first things that can come to mind. You can simply adapt your batch normalization statistics in test time. We had, of course, to tailor it a little bit, and we did it in a way that we would trust more and more the statistics of our test time data as you see more data to be testing. But it was working really well. This is simply some results, and simply this shows the algorithm operating as it improves during seconds, and those different curves correspond to different time scales that you can define as adaptation strategies. But I won't simply, given 10 minutes, I won't simply to show you that yes, it's working. But of course, we wanted also to do some changing the parameters, and here our strategy was simply, well, let's store the data, we use an experience replay buffer. So we store the data, and when we retrieve the data, but with the data that we retrieve, we do an alignment, and also we use it as regularizers, as that you do not forget previous knowledge. We do this on the LoRa parameters, and we align Gaussian mixture models, and long story short, it was working much better than other techniques, and practically so if you look here, for instance, you will see a simple adaptive batch normalization that is quite quick when you do not have enough data. While in this case, you can see that on the right, if you do this and you regularize, you can improve also a bit on unseen sessions. So the system is learning even something in a way. It's learning to be robust. So okay, so after this we were quite happy, but we wanted to face the problem as a progression task. You don't want to classify, but you want actually to control the prosthetic device. And the problem that we have here is that the data set has a lot of, you need to generalize, like it has a lot of different users, and we wanted to generalize from user to user, but the models were failing completely. And so I think everybody here knows meta learning, but simply we used meta learning here, so typical algorithms, and we treat the subjects as different tasks. And thanks to that, we had to a little bit to adapt the model to this case, but we could reach the state-of-the-art performance while adapting with limited data. And now this brings me to what I'm currently working on, that is a bit more fundamental, because I have this interest in meta learning, and I showed you an application of machine learning towards SCMG data. But one thing that I've always been interested about is the fact to using context learning as an efficient form of meta learning. Because, of course, when we use typical algorithms like mammal and reptile or whatever, we use backward propagation, right? So we take the gradients across the whole network. However, it has been shown that if you provide, of course, X and Y as input to a transformer, then it can discover actually a gradient descent process as in context learning. So, and by this result, practically, I think this also explains why a lot of people, like recently Google, have been working a lot of these associative memories and have been implementing this type of test and training strategies, right? And so, from my perspective, that I don't have much resources. To be honest, I work much with smaller models. I wanted to understand if these actually can provide an efficient form of meta learning, and I have only some preliminary results. Really simple mechanistic interpretation. So what we did was to try to understand if actually to what extent you can see this as an optimization process. So what we looked at was, first of all, we tried to look at some form of energy surface for each. So what we did here is that, of course, at this point, if we treat this as adaptation process, if we take this analogy seriously, what should happen is that if we set up the system in a meta learning problem, then adaptation in one self-attention head should kind of minimize the cost function at the end, right? If it's really doing some form of meta learning, there should be this alignment. And so here what we were trying to do first is to try to see if indeed the adaptation induced by these self-attention heads was doing a form of gradient descent. And as you can see, this is the energy surface that we're coming out from there, and they show that yes, kind of. Of course, they do not follow the direction of the perfect direction, but it's still minimizing the cost function at the end. And now here we wanted to understand if somehow we could use transformer architecture, so self-attention, but also test and training architecture for meta learning as an efficient form, and try, rather than doing mammal, where you need to take back propagation to the lower architecture, try to exploit this mechanism directly. And so the idea was, we tried a few toy tasks so far, then we have other results, but they prepared this talk practically this morning, so apologies for that. But I can tell you a little bit, and you can tell me if this direction is interesting, because this is something that we are really exploring. So practically here, simply we are comparing different systems, test and training or self-attention. And what, of course, you can expect is that self-attention is much better at retrieval type of task, while test and training is much better at tasks where you have a more continuous adaptation. So a typical optimization process, because actually you can expect that they are formulated from that perspective. But the thing that I find interesting that we are trying to do is that, of course, from this mechanism, right, because you can derive linear self-attention can actually use any neural network there, right? So what we are doing now is that simply we are doing meta learning with over a CNN, where the CNN adapts thanks to these local objective functions, or over a temporal convolutional network, and we are exploring that possibility. So this is what we have been up to recently. I know there are no results so far. It's working like doing meta learning is a bit more efficient. It does not provide so many advantages in terms of performance, but in terms of efficiency, yes. And we need to test it more. So having said this, I would like to thank you, and any questions or any on this.
Right, thanks.
Yes.
So you